Welcome to the Padhai Karlo JEE preparation channel. Peer Kalpaya Postmanent Maitana channel. You can practice more problems on this exact topic on our Padhai Karlo Android app, link in the description below, or on our website padhaikarlo.com. Today's topic is aromaticity. Let's begin. A compound is genuinely aromatic only when it satisfies three strict conditions. Simultaneously, first, the ring must genuinely be cyclic and fully conjugated, an unbroken chain of alternating, overlapping pure running continuously around the entire ring. Second, the ring must genuinely be planar, or very nearly so, since p orbitals can only actually overlap effectively when they're all aligned in parallel. Third, the ring's total number of pi electrons must genuinely satisfy Huckel's rule, equal to 4n plus 2 for some non-negative whole number n. Benzene, with 6 pi electrons, corresponds to n equals 1. A ring that's genuinely cyclic, conjugated and planar, but has 4n pi electrons instead, matching that author-specific count, is genuinely called antiaromatic, and is actually less stable than an equivalent open-chain structure. Cyclobutadiene, with 4 pi electrons, is the classic example. A ring that fails either the cyclic conjugation requirement, or the planarity requirement, is genuinely simply nonaromatic instead, showing nater aromatic stabilization nor antiaromatic destabilization. Cyclooctatrane, for instance, genuinely adopts the non-PL NR TUB shape specifically to avoid antiaromatic destabilization. Aromaticity genuinely extends beyond just neutral hydrocarbons. The cyclopentadiene anion, with SiX pi electrons after gaining that extra electron, is genuinely aromatic, while the closely related tropylium cation, having lost an electron to leave exactly 6 pi electrons behind, is genuinely aromatic too. Both satisfy Huckel's rule despite carrying a formal charge. Heterocyclic aromatic rings, like pyridine and pyrrole, also genuinely count nitrogen's own contribution carefully. Pyridine's nitrogen lone pair sits in an sp2 orbital in the ring's own plane, not contributing to the aromatic pi system, while pyrrole's nitrogen lone pair instead occupies a p orbital, contributing directly to that aromatic system. The single most frequently tested G skill here is genuinely counting pi electrons carefully and correctly, always checking all three conditions: cyclic conjugation, planarity and Huckel's rule together, before actually classifying a ring as aromatic. A frequently tested trap involves genuinely a ring's LONE pair that's easy to miscount. Always determine whether that specific lone pair sits in the ring's plane, and therefore doesn't count, or in a genuinely perpendicular p orbital, and therefore DOEs count towards the aromatic pi system. Also remember that a charged carbon, whether a carbocation or a carbanion, can genuinely contribute either 0 or 2 pi electrons respectively to that pure close thermal p sahising Paschimi Afriki Rendinavian Leone count. This is exactly why the cyclopentadienyl anion and tropylium cation both end up aromatic despite starting from genuinely non-aromatic neutral precursors. Let's recap. Aromaticity requires a cyclic, fully conjugated, planar ring whose total pi electron count satisfies Huckel's rule. 4n plus 2. Rings with 4n pi electrons under the same conditions are antiaromatic and less stable, while rings failing conjugation or planarity are simply non-aromatic. This extends to charged species like the cyclopentadienyl anion and tropylium cation, and to heterocycles like pyridine and pyrrole, where correctly counting each lone pair's contribution is essential. Carefully checking all three conditions together is the key skill this topic tests. That's aromaticity. Keep Huckel's rule and the lone pair counting distinction sharp. They're the fastest way to handle aromaticity questions on the exam. If this video helped, please like it and subscribe to Padhai Karlo for more JEE preparation content just like this. See you in the next one.